students, welcome to the GATE Academy Power Pack classes. The subject we are going to discuss today is electronic devices and circuits. My name is Santosh. So first of all, I am going to introduce you the agenda behind making these Power Pack classes. We know that the GATE 2019 is very much in the touching distance. Yes or no? We are very close to the GATE examination. Now here we have designed 8 questions in electronic devices and circuits, which is going to cover almost all the important areas of electronic devices and circuits. Okay, so these 8 questions are going to be very important for you. So I'm sure that this is going to be helpful a lot for the serious aspirants who have done very well in their GATE preparation. So ensure that you watch this video from the start till the end without missing anything. And I'm sure that you will be maximum benefited by this particular video. Right. Let us look at the very first question. First of all, I'll start reading the question. A silicon sample is uniformly doped with phosphorus type impurity with a concentration of 10 power 16 per centimeter cube. The electron and hole mobilities are 1400 centimeter square per volt second and 500 centimeter square per volt second. Full stop. If the holes are diffused under low level injection so that the concentration gradient is dP by dx is equal to 10 power 14 per centimeter cube meter. Full stop. If kT by Q is 26 millivolts and there is uniform electric field of 100 millivolt per centimeter, then find option A. The first part of the question is that drift velocity of electrons and holes. Second part of the question is that electron drift current density. Third one is hole diffusion current density. Fourth one is ignoring diffusion of holes. Find the thermal equilibrium values of electrons and holes, where it is given that the value of Ni is 1 into 10 power 10 per centimeter cube. And the last part of the question is that Fermi shift with respect to intrinsic Fermi level. Fermi shift with respect to intrinsic Fermi level. So the very first statement in the question is that you can see the uniformly doped with phosphorus type impurity, but it is not given whether phosphorus is an N-type impurity or a P-type impurity, which is important. So without knowing it's going to be an N-type impurity or P-type impurity, you cannot solve it, because N-type impurity means electron, P-type impurity means hole. So therefore, first of all, you have to understand phosphorus, which type of impurity it is. We will have 2 types of impurities. One is N, the other is P. The N-type impurity are nothing but donor type impurity or the 5th A group elements, which are nitrogen, phosphorus, arsenic, antimony. Whereas in the case of P-type, it's the 3rd A group elements, which are going to be acceptor type impurities, where we are going to have boron, aluminium, gallium and indium. Right. So undoubtedly here what is given is nothing but N-type impurity. So therefore they are going to increase the number of your electrons. Electrons will be the majority charge carriers. Electrons will be the majority charge carriers. So let me write the value of Nd is given to be 10 power 16 per centimeter cube. 10 power 16 per centimeter cube. Electron mobility is given. Mu N is 1400 centimeter square per second. Mu P is given to be 500 centimeter square per second. Per volt second, I'm sorry. We will be having volt second. Now, if the holes are diffused under low level injection, so that the concentration gradient is dP by dx is equal to 10 power 14 per centimeter cube. Okay. Now the kT by Q is 26 millivolts. kT by Q is 26 millivolts. The electric field intensity is given to be 100 millivolt per centimeter. 100 millivolt per centimeter. Now the question is that the first part is that drift velocity of electrons and holes. The first part of the question is that we have to find the drift velocity of electrons and holes. Drift velocity of electrons and holes. So drift velocity of the electrons is given by mu n multiplied by the electric field. Mu n multiplied by the electric field. What is mu n? 1400 multiplied by 100 into 10 power minus 3, which is nothing but 140 centimeter per second. It's going to be 140 centimeter per second. This is nothing but the first part, the drift velocity of the electrons. And similarly, you can find out the drift velocity of the holes to be Vp is equal to mu p multiplied by the electric field. Mu p, what is the value mu p? 500 into 100 into 10 power minus 3, which is going to be 50 centimeter per second. 50 centimeter per second. This is nothing but the first part of the question, drift velocity of electrons and holes. Second part of the question is that we have to find out the drift current density of the electrons. We have to find out drift current density of the electrons. What is the value? Drift current density is going to be sigma n multiplied by the electric field. Sigma n, what is sigma n? N into Q into mu n multiplied by the electric field. And we know the value of n is almost equal to the value of Nd. The value of n is almost going to be equal to the value of Nd, because if you are having 10 power 16, generally in the case of silicon, the intrinsic carrier concentration is going to be 10 power 10. So therefore, according to the mass action law, n into p multitude will be equal to the of Ni square. So therefore, you can see that the concentration of the holes is going to be very low. The concentration of the holes is going to be very low. So the electrons itself will be equal to the value of Nd. The electrons will be itself equal to the value of Nd. So therefore, we can say that it is almost equal to the value of Nd. So let us substitute that. We will have Ndq mu n multiplied by the electric field. What is Nd? Nd is going to be 10 power 16. 1.6 into 10 power minus 19. Mu n multiplied by electric field is nothing but the drift velocity, which is 140. So this is 10 power minus 3 times 1.6 multiplied by 40. What is the value 1.6 multiplied by 40? 224. And 224, what is the unit? Milliampere per centimeter square. It's going to be milliampere per centimeter square. This is nothing but the drift velocity of the electrons. It's the drift velocity of the electrons. This is the second part of the question. There is one more approach to find out that what is the value of the electrons, which is nothing but charge neutrality condition. What does the charge neutrality say? The number of positive charges should be equal to the number of negative charges, or the concentration of positive charge is equal to the concentration of negative charge. What is the total concentration? If I consider two types of dopings, then the total negative charge is going to be N plus Na, which is equal to the of P plus Nd. Okay, so Na is nothing but acceptor type impurity and Nd is nothing but donor type. And we know after ionization, Na is going to become negative ion because it accepts the electron. Nd is going to become a positive ion because it donates one electron. So therefore, because it's a N-type impurity, so therefore there is no contribution of acceptor. So therefore N is almost equal to the of P plus Nd. And you know, the minority carrier concentration is going to be much lesser when compared to the intrinsic carrier concentration. So therefore your value of N is almost equal to the value of Nd. Is almost equal to the value of Nd. So this is important. This is what we call as a charge neutrality condition. The third part is the hole diffusion current density. We have to find out hole diffusion current density. What is hole diffusion current density formula? Jp diffusion current density is going to be equal to minus Q dp by dx, where dp is nothing but the diffusion constant or diffusion coefficient of the holes. So here dp is not given. In this question you can see whether the dp is given or not. The dp is not given. Q we know, dp we don't know, dp by dx is already given in the question. So what we will do is that we will use the Einstein relation, which is nothing but d by mu is equal to vt. So d is equal to mu multiplied by vt. Okay, what is mu? We are talking about the holes, so therefore mu p is given to be 500 and Vt, which is Kt by Q, is equal to the 26 millivolts. So 26 into 10 power minus 3, which is going to be equal to the of 13. So what is the unit of D? Centimeter square per second. Centimeter square per second. This is the value of D, which is 13 centimeter square per second. So once we know the value of diffusion constant, we can easily find out the value of Jp. So Jp is equal to the of minus 1.6 into 10 power minus 19 multiplied by dp, which is 13, multiplied by dp by dx. What is the value of dp by dx? dp by dx is given to be 10 power 14. So we can substitute it. It's going to be 10 power minus 5 multiplied by 1.6 into 13 with a minus sign. So please calculate what is the value. Minus 20.8 into 10 power minus 5, or I can write it as minus 0.208 milliampere per centimeter square. The value of Jp is equal to what? The diffusion current density of the holes is going to be equal to minus 0.208 milliampere per centimeter square. So we have completed 3 parts. Let us go for the 4th part. Ignoring diffusion of the holes. Ignoring the diffusion of the holes, find the thermal equilibrium values of electrons in the holes. Let us give that there is no profile of diffusion which is given in the question. Then we have to find out the thermal equilibrium values of the electrons in the holes. We have already seen that using the charge neutrality condition, the value of the electrons is almost equal to the value of Nd. Okay, so this will be the thermal equilibrium value. The value of N not under thermal equilibrium is almost equal to the value of Nd, which is 10 power 16 per centimeter cube. Now to find out the whole concentration, every time to find out the minority carrier concentration, we use the concept of mass action law. Mass action law says that the product of the concentration of electrons and holes is constant and is equal to the square of intrinsic carrier concentration. So the value of N into P is equal to Ni square. So P is equal to Ni square divided by N. So what is Ni square? 10 power 20 divided by 10 power 16. It is equal to 10 power 4 per centimeter cube. So this is the value of P. The whole concentration is equal to 10 power 4 per centimeter cube. So these are the 2 types of concentrations we are having. One is the electron concentration and the other is the hole concentration under thermal equilibrium. The last part of the question is that Fermi shift with respect to the intrinsic Fermi level. Fermi shift with respect to the intrinsic Fermi level. We know that the Fermi level always gives you the maximum energy of an electron possessed at T is equal to 0 Kelvin. And the important point regarding the Fermi level is how it is going to change with respect to temperature and how it is going to change with respect to doping. And we know when we are talking about an N-type semiconductor, here in this case we have an N-type semiconductor, what happens to the intrinsic Fermi level? Generally in an intrinsic Fermi level, it is going to be at the center of the energy gap. So as you are doping with N-type impurity, it goes up. The Fermi shift is given by EF minus EFI. EF minus EFI, which is equal to the of KT ln of Nd by Ni. It is given by Nd by Ni. What is KT? It is 26 milli electron volt multiplied by ln of Nd by Ni. What is Nd? 10 power 16 divided by 10 power 10. Please calculate this value. So value comes to 0.359 electron volts. 0.359 electron volts, which is almost equal to 0.36 electron volts. This is the value of Fermi shift with respect to the intrinsic Fermi level, and you can see it is a positive value. If it is a positive value, it means that what happens to the intrinsic Fermi level? Let me consider this is the minimum energy level of the conduction band, this is the maximum energy level of the valence band. Here we are having a Fermi level which is intrinsic. Now what happens when you are doping with N-type impurity, your Fermi level is going to be shifted to something like this, EFN. So the shift here is going to be 0.36 electron volts. And Fermi shift is an important concept as far as the gate examination is concerned. So with this we have completed the first question, where the first part of the question is that about the drift velocity, very important formula. Second thing about the drift current density of the electrons. Third one, diffusion current density of the holes. Fourth one, how to find out the minority and majority carrier concentrations under thermal equilibrium. And the fifth part of the question is to calculate the Fermi shift. So now let us do the second question. And the second question is given from the topic of optical excitation. Optical excitation in the GATE examination is very important concept. Time and again we are having the question from this particular topic. So let us see how the different types of questions can be framed on this particular topic. We have again given a single question which covers all the different models. So let me read the question first of all. Consider a semiconductor sample at T is equal to 300 Kelvin. So the temperature is room temperature with a uniform donor density of 3 into 10 power 15 per centimeter cube. So we are having the donor concentration as 3 into 10 power 15 per centimeter cube, optically excited uniformly with a frequency of 345 terahertz. 345 terahertz such that the optical generation rate is 1 into 10 power 19 per centimeter cube second. Full stop. The incident radiation is turned off at T is equal to 0. Assume the low level injection to be valid. The carrier lifetimes are tau P naught is 0.1 microseconds and tau N naught is 0.5 tau P naught is 0.1 microsecond and tau N naught is going to be 0.5 microseconds. Velocity of the light is given to be 3 into 10 power 8 meter per second. So now the thing is that first part of the question is that we have to find the energy gap of the semiconductor sample. Second part of the question is that steady state excess hole concentration due to the optical excitation. And the third part is the hole concentration at T is equal to 0.5 microseconds. Okay, so let me again write down the important data which are given in the question. So I have already told you the topic. The topic is optical excitation. The first part, the first data, given the temperature is 300 Kelvin. Donor density ND is going to be 3 into 10 power 15 per centimeter cube. Frequency of operation is given to be 345 terahertz. It means this is T45 into 10 power 12 hertz. The generation rate is given by 10 power 19. The carrier lifetimes, tau P naught is given to be 0.1 microseconds, tau N naught is given to be 0.5 microseconds. Velocity of light is 3 into 10 power 8 meter per second. The first part of the question is the energy gap of the semiconductor sample. Energy gap of the semiconductor sample. See, there is a formula available. The energy gap of the semiconductor sample is going to be equal to the of 1.24 divided by lambda, where lambda is in micrometers. Where lambda is in micrometers. Is lambda given in the question? Is it mentioned in the question? Lambda is not mentioned in the question. Lambda can be found out using the values of velocity of light and the value of the frequency which is given in the question. So the lambda is going to be equal to the of C by F, which is 3 into 10 power 8 divided by 345 into 10 power 12. So it is 3 by 345 into 10 power minus 4. If you solve it, you will get it as 0.869 micrometers. Okay, so I can consider it to be 0.87 micrometers. This is the value of lambda. Right? So once the value of lambda is known, we can easily find out the value of the energy gap. So the energy gap is going to be 1.24 divided by 0.87. Please find the value what it is going to be. So it is somewhere around 1.425 electron volts. This is the first part of the question. We have successfully found out the energy gap of the semiconductor sample which is given. The energy gap of the semiconductor sample is 1.425 electron volt. The second part of the question is steady state excess hole concentration under optical excitation. We have to find out steady state excess hole concentration under optical excitation. This is the second part of the question. So we know the generation rate G or capital G or small g, whatever it is, given by del P by tau P. del P by tau P. What is del P? Del P is nothing but excess hole concentration. Excess hole concentration under optical excitation. In steady state. Del P is nothing but excess hole concentration under steady state. We wanted to find out this value, which is given by del P is equal to tau P multiplied by the generation rate. What is tau P? 0.1 into 10 power minus 6 multiplied by the generation rate, which is given to be 10 power 19. It is given to be 10 power 19. So the value is going to be 10 power minus 7 into 10 power 19, which is 10 power 12 per centimeter cube. So this is the excess hole concentration under steady state. This is the excess hole concentration under steady state. So the meaning of excess is that generally if you are not doing the optical excitation, we will have the value which is thermally generated holes. Thermally generated holes. The moment you are doing the optical excitation, the hole concentration is going to be increased. There will only be a marginal increase in the electron concentration, but the hole concentration is going to increase for the fact that it's an n-type semiconductor. And in the case of n-type semiconductor, even though the electrons are going to increase, but it is not going to exceed the value of 3 into 10 power 15 under low level injection. But definitely in the case of holes, there will be a very gradual or a drastic increase in the value of the hole concentration. So therefore you can see that excess hole concentration above the thermal equilibrium value is going to be 10 power 12 per centimeter cube, which will be much higher when compared to the actual thermally generated hole concentration. So the last part of the question, let me erase the board first. The last part of the question is the hole concentration at T is equal to 0.5 microseconds. Hole concentration at T is equal to 0.5 microseconds. Right? So we know that we are giving the optical excitation and we are going to stop the optical excitation as T is equal to 0. So if you saw the profile of the hole concentration, so when you switch on the light, the hole concentration is going to increase and then it is going to get saturated, and as you turn off the light at T is equal to 0, they are going to get reduced. So we are finding the value of the hole concentration at 0.5 microseconds. We are finding the value of the hole concentration at 0.5 microsecond, which is given by P of 0 means the hole concentration at T equal to 0 multiplied by e power minus T by tau P. This is the hole concentration with respect to the of time. Okay, and we are indicating only this profile. Okay, so therefore P of 0 will almost be equal to the value of del P, because the general value of the thermal concentration is going to be much lesser. This is the value of del P. So del P is going to dominate, and in this question, because the intrinsic carrier concentration is not given, it is not possible to find out the thermally generated hole concentration. So we are going to negligible it, we can ignore it. Now we can only consider P of 0 is going to be almost equal to the value of del P, which is 10 power 12 multiplied by e power minus T. What is the value of T? T is going to be 0.5 microseconds. 0.5 microseconds divided by tau P. Tau P is nothing but 0.1 microseconds. So micro and micro gets cancelled out. You're going to have 10 power 12 into e power minus 5. So the value of the hole concentration at T is equal to 0.5 microseconds is going to be equal to that of 6.7 into 10 power 9 per centimeter cube. So it's going to be 6.7 into 10 power 9 per centimeter cube. So it's a very important model. All the three parts which we have covered is extremely important as far as the gate examination is concerned. So now I'll erase the board and we will go into the third question. Now let us discuss about the third question. First of all, let me read the question. If a silicon PN junction is operated at a reverse bias of 1.3 volts, the value of the junction capacitance is 5 microfarads. Full stop. The electric field profile in the depletion region of PN junction under equilibrium is shown in the figure below. Full stop. Given the p-type region has a doping concentration of 10 power 15 per centimeter cube, permittivity of the silicon is 10 power minus 12 farad per centimeter. Find the values of, first part of the question is the charge density profile. We have to just draw the charge density profile. Second one is the built-in potential. Third one is doping concentration in n-type region. Fourth one is a peak electric field. Fifth one is the junction capacitance and the depletion region at the reverse bias. Depletion width at the reverse bias of 7.3 volts. Fifth part I will read once again. Junction capacitance at depletion width at reverse bias of 7.3 volts. So we can see that the electric field profile in the depletion region has been given. The electric field profile in the depletion region. So this is the electric field profile under equilibrium without applying any bias. We didn't apply any bias and we have seen that the electric field profile is going to be something like this. So we know if it is positive here and it is negative, it is going down here, it is going up here. It means that this side is going to be a n-type region and this side is going to be a p-type region. You can get more clarity when you draw the charge density profile. So what is the relation between the charge density and the electric field? So just to get the profile, if you are differentiating the electric field profile, then we will get the charge density profile. Okay, the charge density divided by epsilon is what we call as the dE by dx. So the charge density, let me call it as P, is going to be epsilon dE by dx. This is the charge density profile. Right? So if I differentiate it, you can see that every time I differentiate any function, what am I going to get? If I differentiate any function, I am going to get the slope of it. And you can see here the slope is positive. And here the slope is negative. So the profile is going to be like this. And you can calculate the slope, whatever slope you are having. The same slope you are going to have here multiplied by epsilon is nothing but your P. So whatever slope you are having here multiplied by epsilon, you will be getting the charge density profile here. And same here also, the charge density profile here. Right? So please tell me what is the slope here? The slope for here is going to be 10 power 4 divided by 0.4. And here it is going to be 10 power 4 divided by 1. Right? So we can consider it as to be 2 by 5 or 5 by 2. 2.5 into 10 power 4 multiplied by epsilon. Whereas here it's going to be minus 10 power 4 multiplied by epsilon. So this is our charge density profile, which is starting from minus 0.4 to the value of 1. When you look at the charge density profile, you will understand you are having positive charge density here and negative charge density here. We know this is the depletion region. Whatever profile we are drawing here is nothing but the depletion region. When the depletion region is going to have positive charge density, it means that you are having donor concentration here or donor ions here. It means this is going to be n-type and this side is going to be the p-type. It is going to be n-type here and it is going to be p-type here. So n-type means that the value of xn is going to be 0.4 micrometers, and the value of xp is going to be 1 micrometer. So what is xn and xp values? Xn and xp are nothing but the depletion width in the N region and the depletion width in the P region. The depletion width in the N region is going to be given by 0.4 micrometers. It's given by 0.4 micrometers. Depletion region in the P side is given by 1 micrometer. So this is the data that I'm getting. Once I understand that here I'm going to have a positive charge density and here I'm going to have negative charge density. And negative charge density we will always have in the acceptor or P-type region, and I'm going to have the positive charge in the or positive charge density in the N-type or the donor region. So this is the data that I got, from which I can calculate the depletion width under equilibrium. No bias. I'm not applying any bias. No bias is going to be xn plus xp. The total width is going to be equal to 1.4 micrometers. So we have already done with the first part of the question, which is finding out the charge density profile. And let me tell you, many a times the question has come, recent past, 2016-17, the question has come that given the electric field profile, we have to draw the charge density profile and we should also draw the potential profile. So potential profile you will get when you integrate the electric field. When you differentiate the electric field, you are going to get the charge density profile. So a very important thing is that how to draw, provided one thing is given. Here in this question we have covered the electric field is given and we found out the value of the charge density profile. Similarly, when the electric field is given, if you integrate it, you will get the potential profile. So the graphical representations of electric field, charge density and the potential is very, very important. The second part of the question is that we have to find out the built-in potential or the potential difference in the depletion region. We have to find out the built-in potential or the potential difference in the depletion region. And we know the potential difference in the depletion region is given by V naught is going to be integral E dot dl. So when you integrate the electric field, we will always get the potential difference. If you integrate the electric field, we will always get the potential difference. And what is the potential difference? Integrate is nothing but the area. So when you find out the area, so the area of this is nothing but half into base into height. Half into base. Base is nothing but 1.4 into 10 power minus 4. Note, please note, it is in micrometers, whereas here it is in per centimeter. So I'm trying to convert micrometers into centimeter. Most common mistake that students do is that they try to write directly micrometer is going to be equal to the top 10 power minus 6. No, this is meters. But we want it here in centimeters, 10 power minus 4 centimeters. 1 micrometer is going to be equal to the top 10 power minus 4 centimeters. That is what I am substituting here. 1.4 into 10 power minus 4 multiplied by the height, which is going to be 10 power 4. So what is this value equal to? 0.7, or the value is going to be equal to the top 700 millivolts. The value of the built-in potential or the potential difference in the depletion region is going to be equal to the top 0.7 or 700 millivolts. Again, a very important part of the gate. Okay, time and again the questions have come asking about the built-in potential or the potential difference in the depletion region. I'm sure this part is clear to all. Right, let us go for the third part. What is the third part? Doping concentration in the N-type region. Already in the question the data is given regarding the doping concentration in the P-type region. The doping concentration in the P-type region is given to be Na is equal to the of 10 power 15 per centimeter cube. Already the doping concentration in the P-type region is given to be 10 power 15 per centimeter cube. And what we have to find here? Here we have to find out the doping concentration in the N-type region. We have to find out the doping concentration in the N-type region, which is given by what? We can use Q into Na multiplied by Xp is equal to Q multiplied by Nd multiplied by Xn. It means that the charge density which is present, the total charge density which is present in the depletion region here is going to be equal to the charge density which is present here. The total amount of the charge density which is present in the depletion region in the P-type is equal to the charge density in the N-type. So using that, we can form a particular formula. Very important formula again. Q into Na multiplied by Xp is equal to Q into Nd multiplied by Xn. Q gets cancelled out. Na multiplied by Xp is equal to Nd multiplied by Xn. What is Na? What is the value of Na? Na is given to be 10 power 15 and the value of Xp is 1. Here you are having Nd which is not known to us, and the value of Xn is going to be 0.4. 0.4 is nothing but 2 by 5. If I shift to the other side, I am going to get the value of Nd to be equal to 5 by 2, which is 2.5 into 10 power 15. Okay, this is the value of ND. ND is going to be equal to 2.5 into 10 power 15 per centimeter cube. See, the fourth part of the question is about to find the electric field, the peak electric field. We have to find out the peak electric field. See, the peak electric field is already given in the question. The peak electric field is already given in the question, which is given to be, let me erase this part. Now let us go for the fourth part of the question, which is the peak electric field under equilibrium. You have to find the peak electric field under equilibrium. Under equilibrium means that under no bias. See, it is already given to be 1.4, I mean 10 power 4. It is already given the value of the peak electric field. You can see the maximum value is going to be equal to that of 10 power 4. So we can directly take the value of EP to be equal to 10 power 4, or we can use the formula of the peak electric field, which is again important in the GATE exam. What is that? Q multiplied by Na multiplied by xp divided by epsilon. So 1.6 into 10 power minus 19 multiplied by Na. Na is given to be 10 power 15 multiplied by xp. What is the value of xp? Xp is 1 into 10 power minus 4 divided by epsilon, which is 1.6 into 10 power minus 12. So 1.6 cancelled out. You will have 10 power minus 7 times. So this is going to be 10 power 4 times. Right? So it is going to be 10 power 4 volt per centimeter. This is the value of the peak electric field. This is the value of the peak electric field. So just for the sake of using the formula, I have told you, okay? But whereas to answer this question, it is directly equal to the 10 power 4 volt per centimeter. Okay, you can either use this formula or you can use the formula Q into ND multiplied by Xn divided by epsilon. So both of them are going to yield the same answer, which is going to be equal to the 10 power 4 volt per centimeter. Again, a very important formula in the GATE examination point of view. Now let us go for the fifth part of the question, which is the junction capacitance and the depletion width at the reverse bias of 7.3 volts. So the reverse bias voltage that is applied, reverse bias voltage is going to be 7.3 volts. So let me call it as VR is equal to 7.3 volts. And we know the built-in voltage that we got in this question is 0.7 volts. Width of the depletion region is going to be equal to the of, is proportional to the of the value of the total voltage at the junction. Total voltage at the junction. We know width of the depletion region is going to be 1.4 micrometers when you are applying Vj is just the built-in voltage. What is the value? The built-in voltage is going to be 0.7 volts. And we have to find out the value of W, the depletion width, when you are having the Vj, which is V0 plus Vr. We know that the junction voltage is the sum of the built-in voltage and the reverse bias voltage, which here is going to be 8 volts. So we can use this ratio, W2 by W1, let me call it as 1 and 2 here, W2 by W1 is going to be equal to under root of Vj2 by Vj1, which is going to be under root of 8 by 0.7. This comes to be 3.38. So 3.38 multiplied by W1, which is 0.7 itself. So the value of W2 is going to be 2.36 micrometers. Clear? There is one more question in this particular thing, which is the junction capacitance at the same 7.3 volts. What is the junction capacitance at the same 7.3 volts, for which we can use another data which is given in the question, which is when the value of VR is going to be 1.3 volts, we got the value of the junction capacitance to be 5 picofarads. We got the value of the junction capacitance to be 5 picofarads. So let me consider this is CJ1 and this as CJ2. 7.3 volts is the voltage, and here let me consider it as CJ2. And the reverse bias voltages let me consider as VR1 and VR2. What we know is the junction capacitance is going to be inversely proportional to the drop, the value of Vj, considering that it is equally doped. Okay, so therefore Cj is going to be inversely proportional to the drop under root of J. Okay, so because in both the cases we are using the same doping levels, so therefore Cj2 by Cj1 is going to be under root of Vj1 by Vj2, which is under root of Vj1. What is the value of Vj1? Vj1 is going to be equal to the drop 1.3 plus 0.7. Vj1 is going to be 1.3 plus 0.7, which is 2, and here it is 8. So it is going to be 1 by 2. So Cj2 is going to be Cj1 by 2, which is going to be 2.5 picofarads. It's going to be 2.5 picofarads. This is the junction capacitance when you are applying the reverse bias voltage of 7.3 volts. When you are applying the reverse bias voltage of 7.3 volts. So we have covered almost all the important models which are present in the PN junction diode. Now let us move into the fourth question. Now what is the fourth question? It is based on the concept of solar cell. It is based on the concept of solar cell. Let me read out the question. For a particular intensity of incident light on silicon PN junction at room temperature, the optical power density and photocurrent density are 100 milliwatt per centimeter square and 3 milliampere per centimeter square respectively. The power density is given to be PD is equal to 100 milliwatt per centimeter square, and the value of the current density is given to be 3 milliampere per centimeter square. So both of them are for optical. The room temperature, and it is given that the thermal voltage is going to be 25 millivolts. The open circuit voltage under those conditions is 0.5 volts, and the short circuit current is given to be 150 milliamperes. So this is the data which is given in the question. Now what is asked here is find, first part of the question is fill factor if the maximum output power is 60 milliwatts. If the maximum output power is 60 milliwatts. Second part of the question is that we have to find out the maximum efficiency if the area of cross section is 3 centimeters square. Third part of the question is that if the intensity of incident light is increased by 10 times. If the intensity of incident light is increased by 10 times, then the resultant output voltage is dash. The resultant open circuit voltage is dash. So these are the three questions which are present inside the fourth one. First of all, let us find out the fill factor. The fill factor FF is nothing but equal to the of the maximum output power divided by VOC multiplied by ISC. The maximum output power is the maximum output power is given in the question 60 milliwatts. This is the maximum output power which is given in the question. So 60 milliwatts in the numerator, so 60 multiplied by 10 power minus 3 divided by VOC, which is 1 by 2, ISC, which is 150 into 10 power minus 3. So which is going to be 4 by 5, which is 0.8. The fill factor in this question is equal to that of 0.8. This is the first part of the question. The second part of the question is that maximum efficiency of the area of cross section is 3 centimeter square. The maximum efficiency is given by maximum output power divided by power density of the input multiplied by the area of cross section. So power density, the maximum output power is 16 to 10 power minus 3. 16 to 10 power minus 3. The power density at the input is 100 to 10 power minus 3 multiplied by 0.8. So 10 power minus 3 gets cancelled out. So this is going to be 0.6 times. So 0.6, which is nothing but 3 by 5. And here you're going to have 4 by 5. Which is going to be 0.75. The efficiency of the solar cell is going to be 75%, which is a very, very high value. Generally, the efficiency that we have is going to be very less, around 25% maximum. So this is a very high value, but it is a question that is fine. But actually, the practical efficiency is slightly lesser. So let us do this part C part. So part C is that if we increase the intensity to 10 times, by 10 times, then the resultant open circuit voltage is dash. We know the total current is given by I photon current minus I the dark current. The dark current is generally given by I naught into e power V by Vt minus 1, considering the utility factor to be, ideality factor to be 1. In fact, it is minus Iph plus I naught into e power V by Vt minus 1. This is the total amount of current which is flowing inside your diode, the solar cell. And we know at V is equal to VOC. If you are applying the open circuit voltage, then the maximum current is going to be equal to the top 0. The current which is flowing is going to be equal to the top 0, which implies Iph is equal to the top I naught into e power V by Vt minus 1. So to approximate it, we can consider I naught into e power V by Vt. I naught into e power V by Vt, which is nothing but Iph. So here V is nothing but VOC. So therefore V is nothing but VOC. If you substitute here, we will get VOC is going to be equal to the top Vt ln of Iph by I naught. Okay. So Iph is equal to, almost equal to the top I naught into e power VOC by Vt. So Iph is nothing but I naught into e power VOC by Vt. Now what is given in the question is that you are increasing the photon current by 10 times. If you increase the So if we increase the optical excitation by 10 times, even the current is going to become 10 times. Considering the linear case, even the current is going to be also 10 times. So if I use this relation, Iph2 divided by Iph1, which is 10, using this relation, it's going to be equal to the top e power VOC2 minus VOC1 by Vt. Yes or no? Iph2 divided by Iph1 is equal to I naught gets cancelled out, VOC2 by e power VOC1. So it's going to be e power VOC2 minus VOC1 by Vt, which is equal to the top 10. So therefore, VOC2 minus VOC1 is going to be ln of 10 with Vt. So VOC2 is going to be equal to VOC1 plus Vt ln of 10. You can please calculate the value. VOC1 is already given in the question, 0.5 plus 0.025 ln of 10. So the resultant output voltage is going to be 0.557. The resultant output voltage is going to be 0.557 volts. 0.557 volts. So now let us do the fifth question. This is from bipolar junction transistor. See, relatively, BJT is not so important in the gate examination, but there are some focus areas even in the BJT. So we are going to cover those focus areas. First of all, let me read the question. An NPN BJT has biased in active region. So we are doing it in active region under common emitter configuration with beta is equal to 49. What is beta? Beta is nothing but the current gain under common emitter. And it is also given that the thermal voltage is going to be VT is 25 millivolts. VT is going to be 25 millivolts. Full stop. The injected excess electron concentration in base region is linear. So you can see the profile which is given. The profile of the concentration distribution of excess charge carriers is given to be something like this. The maximum is going to be 10 power 13 and the minimum is going to be 0, and the region covered is 10 power minus 6. I'm sorry, the value is going to be 0.6 micrometers. If the area of the emitter base junction, is 0.001 centimeter square, so the area of cross section has been given here. The mobility is given to be 800 centimeter square per volt second. So what we have to find, the first part of the question is that the collector current, base current and the emitter current. So first of all, let us find out the emitter current. So the emitter current is equal to the top. You can see it's a diffusion current. So the emitter current, you can see the directions also. The direction is given something like this. So here it is given as IE. The emitter current is given by what? dn by dx. We are again using the concept of the diffusion current density. Okay, so it's a density, the current density multiplied by the area. Okay, so again we are using the concept of diffusion current density, which is dn by dx multiplied by area is going to give us what? The emitter current. So emitter current is going to be 10 power minus 3 here in terms of centimeter square. 1.6 into 10 power minus 19. dn is not directly given in the question. What is dn? So dn value is going to be equal to the top mu n multiplied by vt. Mu n is given to be 800 multiplied by vt. So 25 into 0.8. 25 into 0.8. So which is going to be equal to 20. And now dn by dx. What is dn by dx? dn by dx is nothing but the slope of this one. And the slope is going to be minus 10 power 13 divided by 0.6 into 10 power minus 4. So I will take it as 10 power minus 4, not 10 power minus 6, because of the fact that we are ensuring that each and every term is in terms of centimeters. So what happens here? This becomes 10 power 17. So this is 10 power minus 2. This is nothing but 3 by 5. So 3 by 5 means it's going to be 5 by 3. So it is 100 here. 50 into 2. 5 into 20. It's 100. So 100 gets cancelled out here. We're going to have 1.6 by 3. 1.6 by 3 milliamperes. 1.6 by 3 milliamperes with a minus sign. See, we got the emitter current, the value of IE to be equal to the top 16 by 1.6 by 3 milliamperes, which is nothing but 0.533 milliamperes. From here we can find out the value of IC, which is going to be alpha multiplied by IE. And alpha, which is the common base current gain, will be equal to beta by 1 plus beta. Beta by 1 plus beta multiplied by IE. So what is beta by 1 plus beta? 49 by 50. 49 by 50 multiplied by IE. What is IE? IE is going to be 0.533. Please calculate what is the value you're going to get. It's going to be 0.522 milliamperes. This is the value of IC, and the direction is going to be the same. Now we will calculate IB. IB is going to be equal to the of IC minus IB. IE minus IB. IB is going to be equal to the of IE minus IC. So IE is 0.533. 533 minus 0.522. So it is going to be around 0.011 milliamperes, or I can write IB is going to be 11 microamperes. It's going to be 11 microamperes. These are the values of IE, IC and IB. IE, IC and IB. With this we complete the first part of the question. Second part of the question is that we wanted to find out, given the value of beta, we have to find out the values of alpha and gamma. And we already found out the value of alpha. Alpha is going to be 49 by 50. And gamma is going to be 1 plus beta. What is gamma? Gamma is the common collector current gain. Gamma is the common collector current gain, which will be equal to 1 plus beta. What is beta? 49, which is 50. So this is the second part. Third part of the question. Third part of the question is that if the common base reverse saturation current is 0.5 microamperes, the common base reverse saturation current is 0.5 microamperes, then the resultant collector current in microamperes is dash. So till here we didn't consider any reverse saturation current. Till here we didn't consider any reverse saturation current. Now we have to consider the reverse saturation current, and the configuration we are discussing here is the common emitter configuration. In the question it is given that it's a common emitter configuration. In this part it is already given that the reverse saturation current in common base is going to be equal to the of 0.5 microamperes. 0.5 microamperes. So IC is going to be beta IB plus 1 plus beta into ICBO. This is nothing but the reverse saturation current in the common emitter configuration. This is the reverse saturation current in the common emitter configuration. This value we already know, which is 0.522 milliamperes plus ICO. What is ICO? 1 plus beta, which is 50 multiplied by 0.5. So if I write this in terms of microamperes, so in terms of microamperes, this value is going to be 522 plus 25. So it is going to be 537 microamperes. This is going to be 537 microamperes, and it is asked in microamperes. You have to please be careful with the units, okay? In this part, it is given that we want the unit to be in microamperes, and in microamperes it's going to be 537 microamperes. It's going to be 537 microamperes. So this is the answer for the third part of the question. And fourth part of the question is that given the base transport factor to be 0.99, given the base transport factor to be 0.99, we have to find out the emitter injection efficiency. The emitter injection efficiency. You know, alpha, which is the common base current gain, alpha, which is the common base current gain, is going to be equal to the of the common emitter injection efficiency multiplied by the base transport factor. So gamma star is going to be the emitter injection efficiency, and beta star is going to be the base transport factor. So here base transport factor is given, and we have to find out the emitter injection efficiency. Gamma star is going to be equal to the of alpha by beta star. What is alpha? Alpha is 49 by 50 is 0.98 divided by beta star. What is beta star? 0.99. So 0.98 divided by 0.99 is going to be 0.989. So this is the value of the emitter injection efficiency. With this we complete all 4 parts of the fifth question. Please ensure that you have written everything. So let us go for the 6th question. The enhancement mode NMOS transistor is biased in saturation region. So we are having an enhancement mode NMOS transistor biased in saturation region, having the current of 2 milliamperes at the value of VDS, the drain to source voltage of 6 volts. If the drain to source voltage is increased to 8 volts without changing VGS, then the drain current is changed to 2.08 milliamperes. The drain current is changed to 2.08 milliamperes. Assuming, this statement is important, VDS applied is much higher when compared to the value of VGS minus VT. Find option A, the first part of the question is that channel length modulation parameter. So we have to find out the channel length modulation parameter. Second part is a saturation current. We have to find out the saturation current at VDS is equal to VGS minus VT. Third part of the question is output resistance considering the channel length modulation. We have to find out the output resistance considering the channel length modulation. And the fourth part is the drain conductance without considering channel length modulation. We have to find out drain conductance without considering channel length modulation. So we have an NMOS transistor. We have an NMOS transistor. So please read the question carefully. It is given that the current, the drain current is going to be equal to 2 milliamperes when you are applying the value of VDS to be 6 volts. And the drain current in the second case is 2.08 milliamperes when the value of VDS is going to be 8 volts. And the third statement says that the value of VDS is much higher when compared to the value of VGS minus VT. What is VGS minus VT? It is the excess gate voltage above the threshold voltage. It is the excess gate voltage above the threshold voltage, which is the saturation drain to source voltage. It means that your transistor is already saturated. The transistor is already saturated, but what happens to the current is there is a marginal increase in the value of the current because it is having channel length modulation. We know when the value of VDS increases, then we know that the drain current is going to increase slightly marginally because of the channel length modulation. So therefore, otherwise it is going to be constant. If there is no channel length modulation, then the current, the drain current, once it enters into the saturation region, it is going to be a constant value. But because of the channel length modulation, we see that there will be a marginal increase in the drain current. There will be a marginal increase in the value of the drain current. So therefore, it is given, we have extended ourselves more into the saturation region. This is VDS sat. But we are talking about VDS1 and VDS2. VDS1 is somewhere here. And VDS2 is somewhere here. So if you are considering the channel length modulation, if we consider the channel length modulation, then the drain current is going to be the drain saturation current. So saturation current is the current that you are having at the value of VD sat. The drain saturation current multiplied by 1 plus lambda VDS. 1 plus lambda VDS. And we know in the first case you are having ID1 going to be 2 milliamperes. ID sat we don't know, into 1 plus lambda VDS is 6 volts, divided by, if I write the second case, ID1 by ID2, ID1 by ID2, this is ID2, then it is 2.08 milliamperes, and here also divided by IDS sat into 1 plus lambda. Here in this case, the value of the VDS voltage is going to be 8 volts. The value of VDS is going to be 8 volts. So if I cancel out, ID sat is going to get cancelled out. You will have 2.08 divided by 2, which is going to be 1 plus lambda 8 divided by 1 plus lambda 6. This is 1.04. So 1.04 plus lambda into 6.24 is equal to 1 plus lambda 8. So 0.04 is going to be lambda 8 minus 6.24. Please calculate the value of lambda here. So what is lambda? Lambda is the channel length modulation parameter. Lambda is the channel length modulation parameter, and this is what we have to find out. So lambda is 0.04 divided by 8 minus 6.24, which comes out to be equal to lambda is equal to 0.227. 0.0227. This is the value of the channel length modulation parameter. This is the value of channel length modulation parameter. Is it clear? So lambda is nothing but a channel length modulation parameter. This is what we have to find out. Because channel length modulation, how much effect it is going to happen in the drain current. Ideally, I want my drain current to be constant when it enters into the saturation region. But because of channel length modulation, what happens is that you can see a marginal increase in the value. See the reason why I told that this statement, that not assuming the value of VDS is much higher when compared to the value of VGS minus VT, is because once you enter into the saturation, the current is going to be higher. The current is going to be higher. So we should not consider that the initial voltage should be where the current is going to get saturated. To avoid this thing, it is told that the current is already saturated and we are much into the saturation region. That is the meaning of the statement, assuming that the VDS value is much higher when compared to the value of VGS minus VT. Okay. Sometimes what we do, the mistake is that we consider that IDS itself is going to be 2 milliamperes. IDS sat itself is going to be equal to that of 2 milliamperes. To avoid this confusion, he has clearly told that both the voltages that you are applying is much higher when compared to the value of VDS sat. Is much higher when compared to the value of VDS sat. Is it clear? So we got the very first part, which is lambda, which is 0.227. 0.0227. So you can approximate it to the value of 0.023. You can approximate to the value of 0.023. Next one is that we have to find out the saturation current. We have to find out the saturation current. Where the current is going to get saturated, that current is what we call as the saturation current. So let us find out the saturation current here. We can take the first case. So 2 milliamperes. 2 milliamperes is going to be equal to the of ID sat. And we know the value of 1 plus lambda is 0.0227 multiplied by 6. You can take it to the other side. Which implies the value of the ID sat, the saturation current, is going to be 1.76 milliamperes. See, please understand that this is the saturation current which is expected, and we want ideally that the current remains 1.76 even when you are moving into the saturation region. But because of the channel length modulation, we are not going to have the current to be constant. The current is going to be marginally going to increase, and we have seen that here at the value of VDS1 is equal to 6 volts, the current is 2, and when the value of VDS2 is going to be 8 volts, it's 2.08. Okay, so the ideal saturation current we wanted to be 1.76, but practically we have seen that under saturation the current is actually increasing with the of the drain to source voltage. It is increasing with the of drain to source voltage. So this is the second part of the question. Third part of the question is that we have to find out the output resistance considering the channel length modulation. Considering the channel length modulation, we have to find out the output resistance. So because we are inside the saturation region, we can write the formula. This is the actual value of the drain current. So the output resistance is going to be 1 by, the output resistance is going to be dou VDS by dou ID. Dou VDS by dou ID. First of all, I wanted to find out what is the value of dou ID by dou VDS. Dou ID by dou VDS. Dou ID by dou VDS is going to be equal to the of lambda multiplied by ID sat. Lambda multiplied by ID sat, which is 1 by R naught, which is nothing but 1 by R naught, which implies the value of R naught is going to be 1 by lambda ID sat. 1 by lambda ID sat. What is lambda? Lambda is nothing but 0.0227 multiplied by the ID sat. ID sat is nothing but 1.76 milliamperes. So 1.7 milli goes to the numerator, it becomes K. So therefore it is 1000 divided by 0.0227 multiplied by 1.76. Which is around 25 kilo ohms. Which is around 25 kilo ohms. Approximate. The actual value is 25.03 kilo ohms. 25.03 kilo ohms. I am approximating it to 25 kilo ohms. The last part of the question is that what is the drain conductance? See, drain conductance, we already know the output resistance, which is the drain resistance. The drain conductance is nothing but 1 by R naught. But here what is asked? Without considering channel length modulation. Without considering channel length modulation. If you are considering channel length modulation, then it is going to be inverse of this, which is 1 by 25 kilo. Okay, so it's going to be 1 by 25 millimho inverse. It's going to be 1 by 25 millimho inverse. But this is considering the channel length modulation. But if you are not considering the channel length modulation, it means that if the channel length modulation is not going to happen, then your current is going to be constant. If the current is constant, then what happens to the change in the current? See, the value of the drain conductance is nothing but dou ID by dou VDS. Dou ID by dou VDS. See, if you are not having any channel length modulation, the value of lambda is equal to 0. Then it means that this part is completely 1. Then your ID is going to be ID sat. ID is going to be ID sat when you are not considering the channel length modulation. Then the current is saturated to be 1.76 milliamperes. Now, when you wanted to find out the drain conductance, it's nothing but the change in the value of ID with respect to the change in the value of VDS. And we know here the slope is going to be 0. It means that there is no change in the value of ID when you change the value of VDS. If you don't change the value of ID, if you don't change the value of VDS, then there is no change in the value of ID. It means that the dou ID by dou VDS is going to be equal to the of 0. Dou ID by dou VDS is going to be equal to the of 0 once you consider there is no channel length modulation. If you consider channel length modulation, then yes, it's going to be 1 by R naught, which is 1 by 25 kilo ohms. If you are not considering the channel length modulation, then it means that your current is going to be constant. If you are not considering the channel length modulation, then the current is going to be constant is equal to ID sat. And there is no change in it with respect to the of VDS. So dou ID by dou VDS is going to be equal to the of 0. Dou ID by dou VDS is going to be equal to the of 0 if you are not considering the channel length modulation. If you consider it, then it's going to be 1 by R naught, because dou ID by dou VDS, this is nothing but GD. So 1 by R naught is nothing but GD, the drain conductance. The drain conductance considering channel length modulation is this value. If you are not considering the channel length modulation, then the value is going to be equal to what? It's going to be equal to the of 0. So with this we complete this particular problem. You can please note it down. Right, so the high frequency CV characteristic curve of MOS capacitor is shown in the figure. So now we are going to do the question on MOS capacitor. We are going to do the question on MOS capacitor, which belongs to the chapter of MOSFET. So the high frequency CV curve characteristics of the MOS cap is shown in the figure. And the figure is something like this. So here we are given the high frequency CV characteristics of a MOS capacitor. So the threshold voltage, the flat band voltage is given to be 0.8 volts. The maximum capacitance is given to be 200 picofarads and the minimum capacitance is given to be 20 picofarads. And what is the flat band voltage? Flat band voltage, generally what happens is that when the metal and semiconductor work functions are different, whenever the metal and semiconductor work functions are different, then we will always have the band bending which is going to happen. We are always going to have the band bending which is going to happen. And also, sometimes what happens is the oxide layer will have some inbuilt positive charges. The oxide layer will have inbuilt positive charges. To remove the effect of both of them and ensure that the energy levels are uniform and flat. To ensure that the energy levels are uniform and flat, we are going to apply a voltage called as a flat band voltage, at which you are going to have the capacitance which is the flat band capacitance. Threshold voltage, we know, threshold voltage is the minimum amount of the gate to source voltage applied to ensure that you are developing the inversion layer. So initially what happens, when you are starting from here, when you are applying the negative voltage, slowly your capacitance is going to come down, it's going to reach the minimum value and it is going to remain at the minimum value. Okay, so the maximum capacitance is nothing but 200 picofarads given in the question, and the minimum capacitance is going to be 20 picofarads. We are talking about the metal oxide semiconductor capacitor, MOS capacitor. See, we will be having the 200 picofarads, which is nothing but the maximum capacitance, which is the oxide capacitance. And minimum capacitance is going to happen because as you are increasing the voltage, what is happening here? The depletion width is going to increase. As a result of which it is going to have another capacitance, which is the depletion capacitance, and you will observe that your oxide capacitance and the depletion capacitance will be in series. So the total capacitance is going to be what? 1 by C is going to be 1 by C ox plus 1 by C depletion capacitance. This will be the total capacitance. So if you solve, you will have C, which is going to be C dep multiplied by C ox by C dep plus C ox. So as the value of the voltage increases, you will observe that the capacitance value is going to come down and it will reach the minimum value when your depletion width reaches its maximum value. So the questions which are asked here is, the first part is the oxide thickness. We have to find out the oxide thickness, and the other data which are given in the question is the area of cross section of the capacitor is to be 2 into 10 power minus 3 centimeter square. Metal oxide semiconductor work function has been given, but we are not going to use it. The doping concentration is also given to be 2 into 10 power 16 per centimeter cube. The relative permittivities are given. Ri of SiO2, the silicon oxide layer, is going to be 3.9 and the epsilon R of silicon is going to be 12. These are the different data which are available with us. First thing that we are going to find out is the oxide capacitance is going to be dash. What is the value of the oxide capacitance? See, oxide capacitance is given by epsilon OX multiplied by A divided by the drop OX. So TOX is going to be equal to epsilon OX multiplied by A divided by COX. This is the oxide capacitance in terms of farads. Sometimes COX is also given in terms of farad per centimeter square, means capacitance per unit area. But here, because the area is given, they are considering COX to be the oxide capacitance. So epsilon OX is going to be 3.9 into epsilon naught. What is epsilon naught? 8.854 into 10 power minus 14 multiplied by the area of cross section, which is 2 into 10 power minus 3 divided by COX. COX value is nothing but the value of 200 into 10 power minus 12. So 10 power minus 12 gets cancelled out here. You'll have 10 power minus 2. So having 10 power minus 5 If this also goes up, these two zeros, then it becomes 10 power minus 2 here. 2 gets cancelled out. So it's going to be 3.9 into 8.854 into 10 power minus 7. 3.9 into 8.854. 3.9 into 8.854 is going to be 34.5. 34.53 into 10 power minus 7 in terms of centimeters. So it is going to be 34.53 nanometers. 34.53 nanometers. This is the oxide capacitance. This is the oxide thickness, sorry. This is the oxide thickness which is going to be equal to the of 34.53 nanometers. It's going to be equal to the of 34.53 nanometers. The second part of the question is that we have to find out the maximum depletion width thickness. Maximum depletion width thickness. See here, the minimum capacitance is given already. The minimum capacitance is C dip multiplied by COX divided by C dip multiplied plus COX. Right? So therefore, what we can do here, C min, which is 20, which is equal to 200 multiplied by C dip here divided by C dip plus 200. So here this is 10 times. So C dip plus 200 is going to be 10 times that of C dip. So C dip is going to be 200 divided by 9. 200 divided by 9. What is the value of 200 divided by 9? It's going to be 22.22. This is the value of depletion capacitance, which is the minimum value. It's the depletion capacitance, which is given by epsilon A divided by W, which is the maximum depletion region width. So maximum depletion region width is given by epsilon A divided by 22.22 into 10 power minus 12. Please calculate this value. Epsilon value is 8.854 multiplied by 12 into area. What is the area? Area is given to be 2 into 10 power minus 3, isn't it? The value of area is given to be 2 into 10 power minus 3 divided by 22.22 into 10 power minus 12. And of course you have 8.854 into 10 power minus 14. So this is 10 power minus 2 times. So you have 10 power minus 5 here. So let me solve all this part. So 24 multiplied by 8.854. 24 multiplied by 8.854 divided by 22.22. 9.56. 9.56 into 10 power minus 5 centimeters. Okay, so if I want to write in terms of micrometers, okay, so it's going to be 0.956 micrometers. There is a maximum depletion region width thickness. There is a maximum depletion region thickness, which is going to be equal to the of 0.956 micrometers. It's going to be equal to the of 0.956 micrometer. Now let us see the third part of the question, which is the MOS, whether it is N channel or P channel. So you have to understand one thing, that as you are moving towards left, you are crossing the threshold voltage and you are inducing the channel. Generally, in the case of enhancement MOSFET, we will be applying the voltage which is greater than the threshold voltage to ensure that the MOSFET is in the on region. So if you are applying more voltage above the threshold voltage, then the transistor is going to be on. Now you are applying the negative voltage for it. You have to understand, whenever you are applying the negative voltage, then it means that it's going to be a PMOS. It's going to be a PMOS. Okay. So majorly we are having three regions here. This is what we call as the accumulation region of capacitance, and this region is what we call as the depletion region, and this we call as the inversion region. So whenever you are applying the negative voltage to cross the threshold voltage, it is nothing but a PMOS transistor. It's going to be a PMOS transistor. If the curve is exactly opposite, it means if the curve is something like this, then this is indication of a NMOS transistor. This is an indication of a NMOS transistor, because you can see here, this is going to be the threshold voltage, and you are going to apply the voltage which is above the threshold voltage to switch on the transistor. Again, you are applying the positive gate to source voltage. It means that it's going to be a NMOS transistor. If you are applying the negative voltage, it will be a PMOS. So answer for this question is that it's going to be PMOS. Now the fourth part is that, again, it's a theoretical part. Theoretical parts are also very important in the examination point of view, because time and again the questions are coming from MOSCAP, and many times it's going to be a theoretical questions also. If the magnitude of the gate voltage is higher than threshold voltage, whenever the magnitude of the gate voltage is higher than the threshold voltage, then it is going to be what we call as the inversion layer. The three options have been given. One is inversion, the other is accumulation, third one is depletion. Okay, whenever you are applying the magnitude greater than that of the inversion layer, it's going to be greater than the threshold voltage, it's going to be in a inversion region. If it is in the middle, it's going to be depletion region. If it is less, it's going to be an accumulation region. So the answer for this question, because he has asked greater than the threshold voltage, so therefore it is a inversion region. So there is a last part which is given as inversion charge density. We know if you are applying the voltage above the threshold voltage, you are in the inversion region. What you will have in the inversion region? In the inversion region, you are inducing a channel which is of inversion layer, It means if you are considering a PMOS, it means what is a transistor? What is the substrate you are considering? If it's a PMOS, then the substrate is nothing but N channel. The PMOS is going to be, I'll do it once again. The fifth part of the question is that inversion layer charge density. Inversion charge density is proportional to. See, always inversion charge density is going to happen only after crossing the threshold voltage. When you are crossing the threshold voltage, then only you are going to have a inversion layer. It means that the inversion charge density is going to be proportional to the voltage above the threshold voltage. Which voltage? The gate to source voltage above the threshold voltage. So inversion charge density is going to be proportional to the VGS minus VT, because you should have the voltage, the gate to source voltage, in excess of VT. You have to apply the gate to source voltage which is above the value of VT. Then only the inversion charge is going to develop. That is the reason why the inversion charge is going to be proportional to the VGS minus VT. In the options it is given VT, VGS minus VT, VG, none. The answer is VGS minus VT. Why? Because only when you cross the threshold voltage, you are going to have the inversion layer which is going to form. So your voltage should be higher than the value of VGS minus VT. Once you cross the value of VGS minus VT, then only the inversion layer is going to form. Now, as you increase the voltage above it, the inversion layer is going to become stronger and stronger. The amount of charges which are present in it is also going to proportionally increase to the top the VGS minus VT. It's going to proportionally increase to the top VGS minus VT. If your voltage is less than VT, then there is no inversion layer. If it is more than VT, then only there is an inversion layer. More the value of voltage is above VT, more will be the inversion charge. Is that clear? So with this we have completed the 7th question, which is on the MOS capacitor. Again, I want to tell you, MOS capacitor is going to be a most important part of the MOSFET transistor. Okay. So now let us enter into the last question and the final question of the power packed EDC classes. So let us first of all see the question. This is again based on the enhancement MOSFET. So first of all, let me read the question. An ideal current voltage relation of MOSFET is scaled by a constant K such that W, L, VGS, VDS, COX and VT change to KW, KL, KVDS, COX by K and KVT respectively. The effect on drain current, transconductance and output resistance in both linear and saturation region is dash. So first of all, we have to understand we are considering a NMOS transistor, and okay, generally we will consider, it's not given in the question that it's an NMOS transistor, but we will assume it to be a NMOS transistor, and it is given in the question clearly that all your parameters like W, L, VGS, VDS, COX, VT, all these are scaled by the scaling parameter K, and you are having KW, KL, KVGS, KVDS, KCOX, I'm sorry, it's going to be COX by K and KVT. Clear? So these are your values of the parameters that you are having after scaling. Now what is the effect of scaling on the parameters which are drain current, transconductance and output resistance? First we will consider the linear region. In the linear region we know ID is given by mu n COX W by L VGS minus VT into VDS minus VDS square by 2. Right, so this is the value of the drain current. See, once you scale it, then what happens? Let me consider it as ID dash. So ID dash is going to be mu n K COX by K. This is after scaling. COX by K, KW divided by KL, KVGS minus VT. So I have taken K outside of these two, into KVDS minus KVDS whole square divided by 2. So when K comes out, here K's get cancelled out, K square comes outside and it gets cancelled with that of K. So it is going to be K times that of ID. It is going to be K times that of ID. So your ID dash is going to be K times that of ID. Dou ID dash divided by dou VGS, which is the transconductance dash. Okay, this is after scaling. So it is going to be what? Dou ID dash is nothing but K multiplied by ID. So it is K times that of dou ID by dou VGS, which is going to be K times that of ID. Now R naught dash is going to be 1 by dou ID by dou VDS. 1 by dou ID by dou VGS. Can you please tell me what is the value of ID dash? So dou ID dash by dou VDS. So let us find out dou ID dash by dou VDS, which is going to be K times that of dou ID by dou VDS, just like the way we have seen here. Right, so therefore you're going to have R naught dash is going to be equal to the of, right, so 1 by K times that of dou ID by dou VGS. So 1 by K times that of, this part is nothing but 1 by dou ID by dou VDS is what? 1 by dou ID by dou VDS is nothing but R naught. So therefore you're going to have R naught. So R naught by K. Only this part, if you are observing, this is the initial part. Okay, if you haven't scaled it, then you're going to have dou ID by dou VDS. So now because you have scaled it, it's going to be R naught by K. Because you have scaled it, it's going to be R naught by K. So this is the value of R naught dash, which is R naught by K. So this is in the case of the linear region, and you will observe that there is no great change in the case of saturation. Even in the case of saturation, the formula is slightly different. It is 1 by 2 times the of mu n COX W by L VGS minus VT whole square. So the effect is going to remain the same. ID dash if you consider, then 1 by 2 mu n k COX into k W by KL, k times that of VGS minus k VT whole square. So if k comes outside, again it's going to be k times that of ID. Same with that of GM. GM dash is going to be k times that of GM, and R naught dash is going to be, here it is going to be COX by K. It's going to be COX by K. So therefore K gets cancelled out, K square comes outside, K square gets cancelled with that of K, you will only have K here. So R naught dash is going to be equal to that of R naught by K, just like the case of the linear region. So whether it is a linear region or it's a saturation region, okay, the effect on the three parameters we are having is the current is going to become K times, the transconductance is going to become K times, whereas the drain resistance is going to become 1 by K times. The drain resistance is going to become 1 by K times, whether it is going to be a linear region or it's going to be a saturation region. Please note it down. Okay, this question might come into some students' mind that, sir, we have changed the ID to ID dash, but we haven't changed any VGS. We are still giving it as VGS only. Okay, it is the case because VGS is still the independent variable for us. Last statement I want to repeat once again. Okay. See, some of the students might have a question in their mind that why are we not changing VGS here and why are we not changing VDS here? It is because of the simple reason that VGS is an independent variable, VDS is an independent variable, and whenever you want to change the rate of change, of course the ID is a dependent variable which has changed, but independent variable is going to remain the same. But when you are considering a specific cases of VG, here VG is a parameter. If you are considering the specific cases of VG, then you are going to consider K into VGS and K into VDS. But if you are taking the VGS as an independent variable and you want to see the rate of change of ID with respect to VGS, that is nothing but the transconductance. If you want to see the rate of change of your ID with respect to that of VGS, that is nothing but transconductance. We should not change it to VGS dash here and we should not change it to VDS dash here. This is going to remain the same. So with this we completed the series of 8 questions, and in the 8 questions I tried to cover all the most important parts of the electronic devices and circuits. So I am sure that you might have given some around 2 to 2.5 hours, but this 2 to 2.5 hours is going to be the most valuable time that you have spent in learning the concept of ADC and understanding from where the questions are going to come. Okay, so I am sure that this is going to be helpful for all of you, and I wish you all the best in the case of the GATE examination, and you will all do well, and ensure that you are keeping your cool and calm in the examination, because that is the most important aspect. It doesn't matter how much you have prepared, but how much cool you are keeping in your exam and ensuring that you are attentive in the exam is of course going to make a difference in the GATE examination. So with this session, I want to close this session. Thank you all of you for listening.